Declarative concurrent programming with Chymyst. My name is Sergei Winitzki. I work at Workday. Excuse me. We do Scala. This is a side project that I did in my spare time. It's an open source project, and I'll show you the GitHub repository for it. Chymyst is a Scala implementation of the chemical machine paradigm of concurrency. This was invented about 20 years ago, and it is known as joint calculus in the academic world. But actually, it's not a calculus. It's a programming language, which is a domain-specific declarative language for concurrency and parallelism. Largely, it's unknown and unused by the industry or software practitioners. So I'm trying to remedy that. I think it's a great paradigm by making available this open source library. And that's what I'm going to be talking about today. So what problem does it solve? We know that it's hard to write concurrent and parallel code correctly. The reason it's hard is because we use the tools such as callbacks or threads or semaphores or locks and so on. These tools force us to focus on reasoning about state, concurrent state, mutable state, shared state. And it's hard to reason about processes going in parallel and each mutating their state and then somehow coordinating or accessing shared mutable state. It's also very hard to test such programs because programs have non-deterministic runtime behavior. Every time you run them, the result is a little different maybe. And never enough testing. There are race conditions, deadlocks, or live locks. All of this is very tedious and hard, and so people try to avoid this by using a different approach such as using parallel collections, Spark, or using futures, using a.k.a. streams, actors, and the chemical machine is one of these approaches that make concurrency easier. So joint calculus or chemical machine, in my terminology, is the same thing. It's a programming language for concurrency. A typical example of a concurrent problem is the dining philosophers. So how many of you are familiar with dining philosophers? So just, okay, quite a few people. So I got this picture somewhere, and then I actually looked up who these philosophers are. I believe this is Socrates, and this is Confucius or something like that. Anyway, I'm not going to talk about this since most people are familiar. Basically, if you look at Rosetta code, for example, there are solutions for dining philosophers in all kinds of programming languages. So let's look at like C#, okay? Initialize, tear down, write header line, write status line, format, disposable. Okay, I'm kind of lost. Try to get right fork, try to get left fork. It's kind of difficult, right? So that's the kind of thing that's I'm talking about. It's hard. You don't know if their program is right. So I'm going to introduce the style of concurrency that I call the chemistry or chemical style of concurrency, which is the chemical machine implemented by the Chymyst library. And also I'll talk about how the actor model is kind of a precursor to this, or how can you see that the actor model is a little less high level than the chemical machine. So if you're familiar with the actor model, which I assume you all are, you'll appreciate that the chemical machine is easier to use. There are other approaches to declarative concurrent programming, which I'm not going to mention any more than just by name, such as pi calculus, Pi calculus is a little similar to joint calculus, but it's actually harder to use low level compared with joint calculus. Erlang's message passing is the same as a.k.a.'s actors. CSP, the communicating sequential processes, is the basis for concurrency in the Go language, which is also kind of declarative for certain things, but it's also less high level. Finally, software transactional memory is another approach. So how do we understand joint calculus or a chemical machine? So I suggest you think about actors. So actors, you have to start. You have a reference to an actor. You send a message to an actor by reference. What if actors were automatically started? If you don't have to handle references to actors at all, you just send messages. You don't worry about actors existing or running or not existing or not running. You just send messages and everything just works. That's the idea. You don't want to use threads or semaphores or locks or anything. You don't want to use mutable state, shared mutable state. That's what joint calculus gives you. That's what the chemical machine gives you. The concurrency is much easier to reason about, which I'll show on examples. To understand this, however, it's a new paradigm. You need to have some metaphors for understanding how to reason about it. So I have two metaphors for you. So one metaphor is concurrent functions that compute with concurrent data. So this is kind of a purely functional world on concurrency. The second metaphor is a chemical soup with molecules and reactions. So that metaphor is a little more concrete and down to earth, and that's how I like to reason about concurrency in joint calculus or chemical machine. So, but let's go back to this idea of automatically started actors. So how would that work? Well, obviously you send a message and then the actor needs to start consuming that message and working on it. So it's like having a function call that's executed concurrently on a data item. So what does it mean that we make function calls concurrent? Well, several functions will run at once, maybe, and so obviously they should have no shared state, right? So we're thinking functionally. So each function is a pure function, takes some arguments, and concurrently executing functions should obviously work on different instances of data, not on shared instances. So how does the system decide which function to call if you give it a data item? Well, obviously, data items have to be labeled in some way for specific concurrent functions. So that can be implemented if we have a special kind of site where we store these labeled data items and functions, and then the functions will wait for data items to arrive at that site to consume them and start computing their stuff. And then the computed results can be emitted back to that site as, again, new labeled data items. So the operational semantics of this is that concurrent functions are waiting and automatically starting to run whenever their data items are available at the site. And as I said, the different instances of concurrent execution will consume different separate data items. So that's how you would logically design the system if you wanted to impose the requirement that actors are automatically started. Okay, so I have not so much time to dwell on this, but basically if you logically follow what needs to be done, if you want to make actors automatically started, you arrive to joint calculus or the chemical machine. So that's, but I prefer the chemical metaphor, which is that first you imagine the real chemistry, such as the reaction between the hydrochloric acid and sodium hydroxide that gives you the molecule of salt and the molecule of water. So two molecules meet, react, are consumed, and emit two product molecules. So this is how real chemistry works. Now, we're going to do abstract chemistry inspired by how real chemistry works. So abstract chemistry means that we have this imaginary chemical soup that contains instances of abstract molecules, molecules of any kind that we define at will. And then certain sorts of molecules will combine and start a reaction. So for example, we can define abstract chemical laws like this, like molecule A and molecule B react, and the result is a molecule A. Now, obviously, that cannot happen in real chemistry, that just the molecule B disappears. But this is abstract chemistry. We don't need to follow physics here or actual real-world chemistry. It's completely abstract. We define whatever we want, such as molecule A and molecule C react and yield nothing. Both molecules disappear and nothing is emitted back. It's completely fine, because it's completely virtual and abstract chemistry. So here's a diagram that illustrates what I just defined in these laws. Now, the program code will define that molecules A, B, C, and so on exist, and these laws exist. So in initial time, the code will emit some molecules into the soup, and then there will be a runtime system that will run all the available laws, finding molecules that can react, running the reactions, emitting the products back into the soup, and continuing this forever. Now, notice that in chemistry, each pair of molecules reacts in parallel, concurrently with all other molecules. They don't wait for each other. And that is possible because they operate on different data items. So that's the model of concurrency we want to imitate. So imagine we implemented this runtime simulator, the chemical simulator, or the chemical machine. How would we use it to actually perform computations? We need to add some data to this. So we say each molecule now carries a value or a data item, a value of some type, let's say integer. And that will be our concurrent data. So each molecule now has a type of value that it carries. Each reaction that, let's say you have A plus B goes to A. Now A has a value, so this value Z on the product of the reaction has to be computed somehow from the values X and Y on the input molecules. So the function that computes Z out of X and Y is the body of the reaction. This is just analogous to the body of the actor that takes the message data and computes some outgoing message. But here we can have several molecules coming in at once. So this is more general than actors. It's like actors that can wait for several messages to arrive at once. And then, so that's how we are going to simulate computation. So we're going to define the molecules, define all the functions at each reaction, and the molecules that come in and come out. So here's an example code. Actually, I'll show more examples, of course. It's just the first example right here. The site is a function call that declares the reaction site where the molecules and reactions are stored. Then we say A plus B goes to basically A, and Z is computed as some function of X and Y. So X and Y are input values, and Z is output value. And we could have a side effect also in the reaction. That's fine. We can write arbitrary Scala code there, but we don't have to usually. So the semantics is that when the reaction is defined and the molecules are emitted, then the runtime will look for molecules that can be consumed. So, for example, A and B. So it will see whether some A and B has been emitted into the soup at this site. And then, if so, it can start the reaction. A and B will be consumed, instantaneously disappear atomically. So that's a synchronization primitive. And then you compute a new value, and you emit the molecule A with a new value back into the soup. And then, let's say there are more B's in the soup, then this can continue. So the first example would be to have a concurrently running counter. So let's say you have a counter with an integer value. You want to increment and decrement it from different concurrently running processes. And you want this to be safe. So there are no mistakes due to shared state. So here's what you do. The only way to do anything is to define molecules in reactions. So obviously, the counter value must be on some molecule. So let's call this molecule counter. The decrement and increment commands are modeled by emitting molecules. So let's call these decr and incr. And these molecules have a unit value. So we don't need value on them. So let's have a unit value on them, unit type. So then we say a counter molecule reacts with decrement molecule and gives you a counter molecule with decremented value. So the semantics is that both molecules are consumed instantaneously, and then this new molecule is emitted. And the next reaction is that increment will increment the value and do the same thing with the molecules. Now, initially, we emit a counter with value 0. So then we can emit decr and incr concurrently in any amount. And you see, because the semantics of a reaction is that both input molecules must be consumed atomically and at once. There's no way to mix this up. There is no shared state. There is no mutation even. I mean, this is purely functional in a sense. So suppose you have 5 decr molecules and 10 incr molecules, but only one counter molecule. So only one reaction can start at a time, just because the molecules are not there enough to start more than one reaction at a time. So in this way, you completely make it safe. Only one decr or incr will react with counter at any given time. And so there will be never the problem with shared mutable state when one thread starts to increment, another starts to decrement at the same time, and you get an error. So that error is completely impossible. Here's how you write this program in Chymyst. So first you need to define these functions that emit molecules. They are called molecule emitters. And these are defined in the syntax. So counter is integer molecule. This is a unit valued molecule. Then you declare reactions using this go function. And the reactions are defined as if they're partial functions with pattern matching. So in this case, it's very easy and trivial, but in principle, this can be arbitrary Scala code, partial function, pattern match of any kind, with guard conditions, with case classes, with all kinds of things. You can do whatever you want here, except that you only can give one case at a time. Here is the same code as I was writing before here in pseudocode as kind of a chemical notation. And that's how it works. And then finally, so you define these two reactions. You define a reaction site by saying site with these two reactions. This activates the reactions. So after you say site, you can emit these molecules and the reactions will start. So this, until you say site, nothing is running. So these reactions are values. So this is a value of type reaction, which describes the reaction. It does not actually run anything yet. When you say site, you activate these. So this can also be defined in line. So you can just say site and then put this code into here. These are just values. So there's no magic otherwise. Magic happens is that the chemical machine will run behind the scenes. So here's what you do then. You say counter 10, incr, and then finally you wait for things to happen, right? This is all non-blocking. So you say counter 10 is a non-blocking side effect of emitting a molecule into the soup. You say incr is a non-blocking side effect of emitting a molecule incr into the soup. So counter call will return unit. It will emit the molecule. It will return right away. There won't be any wait. So this is all automatically concurrent and automatically non-blocking. So at some point, so after you do this, initially the soup will have maybe this state of having 3 molecules in it, and then it will run and let's see. Yeah, so let's connect these two metaphors just very briefly. So reaction consumes molecules in this chemical machine. It's the same as function consuming input values. So this is how reactions implement concurrent functions. Reaction emits molecules as a result, the same as function returns a result value. Emitting molecule with value is like lifting data into this concurrent site or concurrent world, if you wish. And when you define a reaction, like you did here, that means you're lifting this function into the concurrent world. And so this is how these metaphors are actually the same thing. I prefer to think about it in the chemical terms, but you can also, if you want, think about just concurrent functions and concurrent data. So let me perhaps show you, I have to show you this first. There's one other feature, which is the blocking molecule. So right now, we have seen all molecules are non-blocking. So you emit these molecules into the soup, but you don't wait for anything. There's another thing, another feature of the chemical machine, which is very useful, a blocking molecule, which is a molecule where its emitter will block the calling thread until some reaction starts, consumes this molecule, and returns a value back. So in this way, you can implement blocking wait if you need to. So here's how it works. So you declare an emitter, let's say f, for fetch. So you want to fetch the value of this concurrent counter. And you want to make a blocking fetch. So how do you do that? You declare this as integer and string. Types, so integer is the type of value it carries, and string is the type that comes back, the reply value type. Then you define the reaction like this. Implicitly, this molecule F carries a reply emitter, which you do not put into it when you emit the molecule. So it's automatically included when you actually start the reaction. So you have this reply emitter. So the reaction can use that emitter to emit the reply, computing some value. And that's, for example, will consume the counter C, consume F, and emit the reply. It will not emit molecules back, let's say. So here's how we would use that. You would emit C with value 100, and then you would emit F with value 200. Then you have C and F. This reaction can start. X will be 200, Y will be 100. This will be 300. The string 300 will be on the reply, and that magically will be the result of this blocking call. So this feature allows you to block and wait until something happens, which is useful in tests, perhaps, not very useful in actual code, because you'd like everything to be non-blocking as much as possible. So the first example code that I can show now is that you count many, let's say, increments or decrements until you reach a certain counter value, and then you emit a reply to some blocking molecule, and so you can kind of execute a test waiting until something is done. So let me show you the code for this. So we define a molecule C, molecule Decker, molecule finished, molecule get. Just like I said, this is abstract chemistry. You can define any molecules you want, any number of them. Molecules are not threads. They're just little pieces of data. It's very cheap to define different kinds of molecules or reactions. So there are three reactions now. The first reaction is that this finished molecule reacts with the get molecule and produces a reply to the get. So we will eventually call get, and we hope that the finished molecule exists. So until that exists, the get call will be blocked. The second reaction is that the Decker molecule will decrement only when the value x is positive, and if it's not positive, then no molecule will be emitted. And actually, I would actually write it like this. Maybe this is better. Because then this reaction won't even start if the molecule is with a value x that is not positive. So when the molecule has 0 value, then we emit the finished molecule. Initially, we emit C with value 10,000, and we emit 10,000 decremolecules. So let's see if this runs. We emit 10,000 decremolecules, and when we count down to 0, finally this last reaction will run, finished molecule will be created, it will react with a get molecule, we'll get a reply, and this get will unblock. So this is how the test works. Any questions at this point? Yeah.
Didn't get here at the beginning. This looks like there's a relationship between the RETE algorithm and joint calculus.
The which algorithm?
RETE, R-E-T-E.
Oh, I'm not familiar with that, sorry.
What?
I'm not familiar with that. The question is whether...
It's used in a lot of business rules, systems like rules and others.
The question is whether there's a relationship between the RETE algorithm and joint calculus. We can talk about this after.
While you were talking, I found an article.
All right. Okay. Well, I'm not familiar with those systems, so I cannot comment, unfortunately. All right. So, so this is how it works. Another interesting thing about implementing the chemical machine as part of Scala, as a DSL in Scala, is that we can use all the features of Scala, all the functional programming features, local scopes, types. Everything is just transparent. The primitives that I gave you is the entire new thing that is added. So there are these molecules and reactions. They're completely orthogonal to whatever programming language you embed them into. You can do this in C, in Python, in whatever. It's completely orthogonal. But we're embedding it in Scala, so we have great functional programming features. So for example, we can have a molecule with this type. The type of value that it carries is an emitter, is another molecule. So we can do whatever we want, and it's all type safe. We can also define molecules in local scope. So the result is that we can make this counter example of the concurrent counter that I made. And we can define all of this chemistry in the local scope of some function. The function will return the emitters for the molecules deca and get, but it will not return the emitter for the molecule C. And the result of that is the outside code can make a counter, so it will create this counter C and emit it, but the outside code does not have any access to this counter. It's completely encapsulated. So it can get the value, it can decrement the counter, but it cannot screw up with the chemistry. So an example of screwing up would be to emit 5 more molecules C with different values. So that will completely derail this logic, because then the decre molecule will react with any of these counters, and the get molecule will react with some other counter, perhaps. So this whole idea of counting just breaks down if you have different copies or different instances of the molecule C at the same time. So we have to guarantee that C is emitted only once. It's very easy to guarantee if you put that into local scope. So because local scope is tightly encapsulated, we get a benefit that's completely independent of joint calculus. So that's why I say it's functional programming plus joint calculus. Joint calculus is kind of neutral to the language you're embedding it into. I made previously joint calculus implementation in Objective-C for iOS and in Java on Android. It's ugly, but it works. It's completely orthogonal to your language. So Scala is a great language for doing this. you can have very nice and visual syntax. So there are more examples I can show. For instance, this example, I can implement future in terms of molecules. And I say future of, and that's that's similar to having a future. I can implement MapReduce. In the interest of time, I will skip this for now, but basically, the way you reason about it is that you imagine what molecules need to be present. So for example, for MapReduce, you want to put data on a bunch of molecules, and each molecule will start a reaction, and that will start automatically in parallel. And then at the end, you want some other molecule to react with the results and gather the results and aggregate them. So you just think about this visually like that, and you get your MapReduce. Finally, I want to show the example of dining philosophers. Now, you see what happens with dining philosophers is that I define molecules that represent a thinking philosopher and a hungry philosopher. And then I write these reactions between these molecules. So for example, thinking philosopher is this molecule. It reacts just by itself, doesn't need any other molecules to start a reaction. And it starts to think, well, it thinks for some time, and then it emits a molecule with a hungry philosopher. And so on for other philosophers. And here is the hungry philosopher, takes two forks next to it, next to the philosopher, and then starts eating, and then starts thinking, puts down the fork, puts down the other fork. Now this is the entire code. I mean, I showed you the C# result before, but here's the executable code, right? So this is the app. These are the functions that think and eat. These are definitions of molecules. This is the code that I'm done. You see, this is completely declarative. I can run this, and you'll see what happens. So that's the power of joint calculus, or the chemical machine. It gives you a declarative solution for concurrent problems. So let me very briefly run the comparison again with actors. So the main difference between actors and the joint calculus is that in actors, message emitters are specific to each actor reference. In joint calculus, message emitters are specific to data. So for example, in actors, you have two actor references. We need to send each one of them a message. Here, we define reactions between data. So data X is labeled by A, Y is labeled by B, and B can be consumed by different processes. And so message emitters are really specific to data, not to processes. It's much easier to reason about data that is present, than to reason about processes that run and change their state as they run, or they terminate, or they didn't yet terminate. It's much harder to reason about that. I'll skip in the interest of time, but there's an interesting example of a concurrent merge sort algorithm, which works by initiating a chain reaction. So the merge sort on an initial array initiates reactions for merge sorts on the partial arrays, and they initiate their own child reactions. And so that dynamically creates a tree of reactions. When everything is done, you have the entire array sorted, and the parallelism is automatic. This is the code. You see, it's very short. I define a reaction here, a new site, a new molecule, inside the reaction here. So the ones that I set in brown or yellow, they are defined recursively. So it's a reaction that defines recursively a different reaction inside it, and that runs that, which defines again new reactions. The entire code is here. This is the entire code, the perform merge sort. So I don't have time to explain step by step how this works, but the idea is that it's a chain reaction that recursively creates more reactions, and all of this is completely static, type checked, type safe, and yet dynamic in the sense that you can create any number of new reactions and new molecules depending on data. All right, so there are other things that I would want to say, but one thing is that I'd like to say don't look at the Wikipedia page, okay? Just don't look there. If you want to learn about joint calculus, don't read this. I don't understand a word of this. I mean, look. Communication occurs only on defined names, okay? You got it, right? I mean, it doesn't occur on undefined names, right? Okay, anyway, unfortunately, joint calculus is this thing where they have this special jargon. I prefer the chemistry terminology. They have this terminology, so I have a dictionary here for you. There are many previous implementations. Only one of them is actually useful, which is the JoeCamel, which is a maintained fork of a.k.a. compiler. So I'm trying to make this useful for the Scala community, and you're welcome and encouraged to check out my repository, which is this one. So please let me know if you are interested, and I think I'll just stop here because I'd like you to think about it and ask me some questions. Thank you. Yes.
When you have reactions that can trigger, when you have enough molecules that can trigger different reactions, how do you choose these reactions?
So the question is, if I have different molecules that can trigger different reactions, how are they chosen, the reactions? So this is non-deterministic. So if you have, let's say, molecule A, so counter can react with decrement and increment. And what if you have all of them at once? So this is non-deterministic. So there are certain ways of controlling this, but basically it means you are facing non-determinism and you should face it. You should organize the chemistry such that the molecules react in the way you want. You should not depend, there are no way to say priorities, set priorities on reactions or molecules, and it will be self-defeating if you did so. You should face non-determinism, make your code so tight, and it's easy to do with molecules, much easier than with other paradigms. But you have to do it, you have to face it.
Are the molecules emitted in order? Like,
so the question is, are the reactions triggered in the order molecules are emitted? So I didn't show this slide much. This slide shows you under what conditions that is true. So there's an automatic optimization where there's static analysis on the code that you wrote, and it determines whether certain molecules can be consumed in the order they're emitted without breaking down the semantics. Because that sometimes can break down the semantics. But basically, you can check that this is so in your code, and if you need that, you can make it so.
Just wondering, probably related that to YAML where
How do I relate to what?
Yeah, so just taking all the calls that are available for implementation, or is there a way
So, okay, the question is, are all the cores used automatically, or is there a way to fine-tune that? So I have features to specify thread pools for specific reaction sites, or even for specific reactions. So if you need some reaction to be high priority, low latency, you can do that by creating a high priority, low latency thread pool and using that. I do not directly control cores. All cores are used. So it's, it's the Java thing. One last question, maybe.
Do you have a sense of order of magnitude for what the cost of a molecule is. I mean, I have an application where I could conceivably putting a few hundred million molecules in and running it on a really large instance. Are there nonlinear?
So the question is the scaling with the number of molecules. So how does it scale and what are the constraints and 100 million molecules. So molecules are data on a heap and they're not threads. The number of threads can be 5 and you can run. So basically each molecule is a small data structure. I have not particularly optimized right now for this use case. I cannot tell you exactly how many megabytes you need for 100 million molecules, but they're just data structures in the heap, on the heap. So I could probably, and there are some, if the molecule's data is very simple, then it's stored in a hash map. If it's not a huge amount of data on each molecule, then you can have hundreds of millions of molecules easily. Thank you very much.